So let's do a first try. So here now I actually do have a recursive definition of factorial, where the definition of factorial includes another procedure call, in this case to itself, with an argument that's numerically smaller. And since the argument gets smaller each time, the recursion eventually terminates. And you can see the test for the termination of the recursion. Basically, when n gets to 0, we return 1, no more recursive calls. And you can sort of see that playing out here. In other words, to compute fact of 4, I'm going to have to first compute fact of 3, so forth and so on. Okay. So let's try a very simple set of conventions, and these will actually fail on a variety of fronts. And we'll debug that, and we'll come up with a more sophisticated strategy for compiling procedure calls. But we have lots of registers, so why don't we just use registers? We'll just sort of, always programmers can invent whatever conventions they want, particularly around the use of registers, because they're there for you to use. And you can say, okay, I'm always going to use this register for this and that register for that. So what I'm going to do is to have a convention where I put the argument, in this case, the single argument, into R1. And now you can say, well, what about procedures that take 2 arguments? Well, use R1 and R2. What about procedures that take 17 arguments? How about R1 through R17? What about procedures that take 112 arguments? And then you can sort of see, well, maybe this isn't the best strategy. It was convenient when there's a small number of arguments, but for arbitrary number of arguments, we'll probably have to come up with something more sophisticated. When, let's say you are going to be, you're a big program and you're calling me to do something specific for you. I'm the procedure. So when one of you calls me and says, Chris, could you please compute factorial of 3? I'll need to know which one of you to return the answer to, and then you'll resume execution, right, after I'm done with my job and hand, if you will, the baton back to you. The thing is that we need to have some convention, and not only do I need to know what argument you want me to compute factorial of, you need to give me some information about where to go back to when I'm done. So typically, at a minimum, you need to pass me a return address, a PC that I'll jump to, that I'll put into the program counter, a value I'll put into the program counter when I'm done, which is where execution will resume when the procedure exits. So we're going to put that address into R28, so that's going to be another register that we're going to allocate. So we have, let's take a little list of registers here. So R31 is always 0. So here I'm talking about using R28 to basically always hold the return program counter. And we'll actually give this a special name. It's called the linkage pointer. So it's telling me where I go to after I'm done. Okay, and then finally we're going to have a convention that we're going to use R0 for the return value. So when I compute the actual answer, where do I put it so that you know where to find it? And I'll just stick it in R0. So you'll just assume that when I return control to this program counter, typically almost immediately following, there are some instructions that will use the value in R0 as the result of the procedure call. So here's the compilation that's been done using that convention and some of the techniques we just worked on last time. So here's a procedure call. We're going to move the argument 3 into R1. That was our convention. And then we're going to use the branch instruction, in this case an unconditional branch, this is the destination here, fact. So the next instruction to be executed, so we're going to do the branch, and the next instruction to be executed is going to be that compare less than or equal to constant. So this transfers control from this location in the program to this location, and at the same time remembers the address of the halt instruction in R28. So remember, the branch tests a value, in this case the BR instruction really is doing a BEQ on R31. BEQ is actually the instruction we have. So it's testing to see if R31 is 0. In fact, it is. So it's going to do the branch. So not only does it transfer control, but in R28 in this case, I'm going to make a little note down here, it puts in the address of the halt instruction. Okay, and it's actually what it puts in is the address of the instruction following the branch. So if you go back and look at what branch does, the thing it sticks into the destination register, this R28, is the address of the following instruction. And you can see why we designed it that way, because we intended branch to be used for procedure call. And we set it up so not only does it transfer control, but at the same time it remembers where execution should resume when the factorial procedure returns. So everybody sort of get the idea here? I'm passing two things in, the argument in R1, and in R28 I have the address in memory of an instruction where I want execution to resume when jump is done. Okay, so now if we go ahead and look inside of the factorial routine, it's going to start using R1 because it was compiled to know that the argument was in R1. That was our convention. So any reference to n, the compiler knows to say, well, that's going to be in R1. I'll just go ahead and use that. So it tests to see if it's 0. And if it's true, it goes down here, where it's going to move a 1 in, and I'll talk about the jump in just a second. Here's a recursive call, and remember our convention, so n minus 1, so well, up here I've moved R1 into R2 to save away a copy of n, because I need to make a recursive call which is going to reuse R1, but notice I need to use n after the recursive call returns. So as the assembly language programmer, the compiler has to say, wait, I need n, so I'm going to save myself a copy of it, and then compute n minus 1 in R1 and do that recursive call. Okay, so I'm following the same calling conventions to make that second call to factorial, that nested call to factorial. And when I come back, I'll go ahead and take the result that came back in R0, and I will multiply it by the saved value of R2, which is the value of n. So that would be n times factorial of n minus 1. That's what that multiplication is doing, because factorial of n minus 1 will be in R0 when the procedure call returns, and R2 is where I saved my copy of n. And then finally, I come along here, and this jump instruction, the one instruction I didn't describe to you before, is I can say jump, and then typically give a name of a register. Okay, this one actually. Jump is like branch in the sense that it saves the address of the next instruction into that destination register, but R31 means we're just throwing it away. But what jump does is to take the value of that register and stick it in the PC. So this takes the contents of reg RA, in this case R28, and simply sticks it into the program counter. So there's nothing conditional about it. It's not testing any values. It just says, take this number and stick it in the program counter. And the number I want to stick in the program counter is the value I passed in R28. So that's where I wanted execution to resume. There's a couple flies in our ointment here. Okay, so notice that when we did the recursive call, we actually replaced this address that was in R28. And what address did we put into R28 instead? Right, we actually put in the address of that multiply, which was the instruction that followed this branch. And that was, we're all following our convention here, but now you can see there's some bogosities in our convention. What was the problem? The problem is that we've been reused R28 in the middle of the procedure, and in so doing, we wiped out where we're supposed to return to. Right, so that's one thing. The other thing is, notice about R2 here. What I've done is I've carefully saved a value into R2, hoping it will be there after I make my recursive call. Right? I mean, you can see I carefully put something in R2 here, and then I expect it to be there after the recursive call. Will it be? Yeah, when I called factorial, it said, wait, I get to use R2. And you're saying, no, I'm using R2. And then you say, wait, we're the same guy. You know, we have to make up our mind collectively here to sort of figure out that we have to have a convention about registers. And there's sort of two obvious conventions. One is that when you call me to do something, I can use any register I want, which means, and then you can't rely on the value of any register, which means you can never leave anything in the registers that you expect to find there when the call returns. Or the other convention is that I can't use any register but R0. I mean, R0 is already known to be changing, but any other register that I want to use, I have to save its value, then I can use the register, then I put back the old value I was. So there's a sort of notion of, can you rely on the register contents being the same or not? So that's a convention we're going to have to decide on. Okay, this convention here of assuming that I can use the registers but then not saving their values just means that register values will disappear on me when I make procedure calls. So this procedure here clearly, this compiler here was clearly a little confused over, can I expect R2 to be there or not? And it was inconsistent. It expected it, but then it didn't produce code that actually made that expectation true. Okay. So we pointed out the R28 problem, we have the R2 problem. So this convention, although maybe simple, and it gets the basics, you can sort of see all the things we'll have to keep track of, although simple, we're not getting all the job done we want to.